Okay, double integrals over general regions. So as I implied, we can't just rely on having a rectangular region. So let's get to more generalized things. Sketch the described regions of integration for these first two, and that's all it is. And these are very easy ones overall. So the reason you do this is because it makes it a lot, it's a lot harder to just sometimes guess what that you'll see, the direction, but like when you're actually integrating, you have to kind of pay attention to which direction the cross sections are being taken and stuff. So 0 to 3, 0 to 2x. So yeah, 0 and so x is just the x equals 3 and x equals 0 are bound things here. 3 and 0 here. And y equals 0. So it's just going to be this one little, the bounded area. You can already tell from those three alone it's going to be a triangle of some sort, probably. Because it's just a line 2x. And you plug in the points. I think that's one of the general ways is if you want to find an actual pretty decent graph, just plug in points when it's like this. X equals 0, x equals 3 means it's 0 and 6 are your y values. So 0 here and 6 here. This would be the point 3, 6 and the point 0, 0. And the point here would be like 3, 0. Yeah. That's what, it's a triangle though, the region. And here it's a little bit more of a curve. 3 minus, so numbers, it's negative 2 to 2 is y. So y is given by y equals negative 2 and y equals 2 for its bounds. And x equals 4 is a bound here, and x equals y squared. So x equals y squared is going to be, I mean, you could technically graph y equals square root of x as well on a calculator. Make sure you get the positive and the negative parts of them. Like, you can use a graphing calculator really for, I think, a good deal of this stuff. You don't really have to know how to graph like some of the functions by hand if you really needed to, like good and then write down a sketch of that. You would have to, but it's important to write it out so you can at least see the direction a little bit. You'll see. But yeah. But x equals y squared is kind of not that hard to figure out, especially when it's just y squared. It's like it's a parabola, and it makes sense it would be like this, because when y equals 0, x is 0. So then basically if you had y equals 1 and 2 and going on, it would get bigger value of x. Same with this. Like negative 1 squared is 1, 1 squared is 1, so your x values are going to always be positive. Because x equals y squared. And negative 2 and negative 4 gives you, yeah, they both end up at 4 if you want to plug them in and see. You could also check for 0, but I think that's pretty obvious. But that's your graphs. That's sketching, that's making a quick sketch. Now it's time to do one where it matters more. We have to write an iterated integral for this, just this simple area one over the described region R using vertical cross sections and horizontal. So that's basically like your two types of double integrals here when you're on the plane like this, when you do an x and y rectangular coordinates. You're going to have to choose if you want to do x or y focused. Where it's going to be x, function, or y, function where y is described by x, or x described by y, or whatever. But that's the best way. So sketches can vary in like how good they are, but just to get an idea. So it's good. It's helpful to sketch it though. So we got bounded by y equals square root of x, y equals 0, and x equals 9. X equals 9, y equals 0. Those are simple. Y equals square root of x though. Yeah, it's kind of like squared. You could write it as x. You could say it's x equals y squared like before. Or you can plug it into calculator or x squared root of x, and it's just a positive. Remember that. Well, in this case at least. I guess technically you could also do it down here, but it would not be part of the bounded region. Just be the positive ones. Let's not focus on that. Why? So y equals 0 means that square root of x equals 0, which implies that x equals, so that's only point A, and they meet. Yeah, point of intersection is just the origin. So the x limits can be thought of as x equals 0 and x equals 9 for this one, if we're going to do y equals square root of x, y equals 0 for 1. So that's what it is. In the region we described as that, such, and it's 0 to 9, 0 to square root of x, and that's dy dx. That's a vertical. And you do this because y equals 0, y equals square root of x, you go upwards from bottom to top. So this is below this function always, so yep, bottom to top. Horizontal, you go left to right, from the leftmost part to the right. So it begins on the left. So let's see what this is. So for B now, x gets integrated first and all that. For horizontal, vertical, y is integrated first, and it's like this form. Square root of x is the upper limit, 0 is the lower, because it goes from 0 to square root of x. The region upwards. Up, up, up. Now we go from left to right for x, for the horizontal course sections. So we have to write this as a function as well. So y equals square root of x means that x equals y squared. And this will be the lower limit, and we'll see, because x equals 9 is the other limit. X equals 9, x equals y squared. So why is y equals y squared, x equals y squared now the lower limit in this case? We're doing it, well, precisely because we're going from left to right. And I can sometimes get confused and I scribble stuff out. But I sometimes even get confused when I'm not thinking. So x equals 9 is all the way over here. So the leftmost part would definitely be x equals y squared. And what is going to be at y equals 0 is going to be the lower limit, and y equals, because that's like a bum. And y equals 3. You can, by plugging in x equals 9, that means y squared equals x, which means, and you can do it like that and get 3. We can just do y equals square root of x and have y equals square root of 9 from the beginning. So 0 to 3 is the bound for y, and y squared to 9 is the bound for x. And dx dy. And that's how you do it. Those are equivalent to each other. You get the same result. Now it's time for this one. Bounded by y equals e to the negative x, y equals 1, and x equals ln 3. So this one. Yeah, I'm sorry it takes a little bit of time. I want to go slow and make sure this makes sense. Because this is kind of tricky compared to other stuff, because you actually do have to do some thinking about what's going on. Y equals e to the negative x, you can use this as a calculator, but it's going to be downward sloping, but it never hits 0. I mean, it does eventually. The limit is, as you approach infinity, it'll become 0. But it's never going to actually approach under normal. You're not going to see it, especially with our frame of reference. It's not going to be 0. But yeah, the limit will be 0. Limit to infinity. Oh, y equals e to the x, y equals y, x equals ln 3. You have to do both cross sections again this time. Y equals 1 down here. Y equals e to negative x. They intersect at the point where, e to the negative x equals 1 is a point of intersection for these two. That means ln e plug natural log, so basically negative x when you do that, because e cancels, so negative x equals natural log of 1, which is 0. So then it's x equals 0. So when x equals 0 is the point of intersection for them. And that's when e to the x equals 1. Y equals 1 is just this horizontal line. And x equals ln 3 that way, and obviously so x equals 0 is going to be in your lower limit for x. So the vertical e to the negative x is on the bottom. 1 is the top upper limit, because y equals 1, y equals 0, because it's obvious going up. From bottom to top. Yep, bottom to top, that's your vertical cross sections. Now b, y equals e to negative x means ln y equals ln e to negative x. So yeah, x equals eventually negative ln y. Basically, we have y equals 1/3 for x equals ln 3. Plug it in. Yeah, I'm kind of messed, but it works out. Whatever, I don't know if that's the best way to solve it, but I'm just thinking, 1/3 will be your, just plug in and figure out what it's, so ln third, what does x equal ln 3 give you? That's like the end of it for y. And of course 1 is the other one, y equals 1. So 1, so that's simple, and like, so x can be between ln 3, which is solid end, and this x equals negative ln y. So negative ln y will be the bottom, because it's this function, and ln 3 is all the way out here on the right. So left to right, yeah. And dx dy this time, because not dy dx is for the vertical way, dx dy is horizontal. I'm hoping this makes sense. Ugh. 19 and 23. Sketch the region of integration and evaluate the integral. So you have sketch and then evaluate. So you're given this the integrals here. X sine y dy dx. Sketch the region of integration. So we have 0 to pi and 0 to x. So y equals x. Y equals 0. X equals pi. X equals 0. It's triangle. And pi will be one of the points. And it's obvious though. When you evaluate this, just do it like normal. So with respect to y, it becomes negative cosine y. Y equals x, y equals 0. Oh, that's the palm. Second integral, and you get to this. So you get x times negative cosine x plus 1, or 1 minus cosine x, whatever. Point is that it's dx. We can't really evaluate this, unfortunately. This is good, because we'll get x times, negative x cosine x plus x. Yeah, because we can't really. I suppose we could at least evaluate the x, but we could separate it so we just have to worry about x and negative x cosine x. And we could probably do that by parts, but we might as well do the whole thing by parts, I guess. Because we can't avoid integration by parts. X cosine x or negative x cosine x, whichever one, those two both types. That's something that we can't integrate with our usual methods. So we have to use one of the special methods like integration by parts. So we have u dv, the integral of that equals uv minus integral of v du. So you let u equal x here, and dv is also part of this original integral, so negative cosine x plus 1 dx. U is the one little part usually, and dv is everything else. The u equals dx here, because that's what derivative of u is just du, and x is dx here, because it's 1 times dx. And v equals the integral of vv, given you get from the palm. So it becomes negative sine x plus x, so x minus sine x, because you have v. And you plug it in, x times x minus sine x minus integral of x minus sine x dx. You can integrate this at least. So eventually you get x squared over 2 minus x sine x minus cosine x. And that's the you don't know, so this integral here equals that. Just the limits. We have to add in the limits now. do all the work, and you get pi squared over 2 plus 2. That's an acceptable answer. You can estimate it. You can plug in pi squared, divide by, pi squareds, and divide by 2, and then add 2. And you'll get it. You'll get an exact, well, estimated answer, to 3 or 4 digits or whatever, decimal points. I just think it's fine to leave it as is for at least this. I don't like to use a calculator myself, and especially use stuff like this unless I absolutely have to. That's one of the things I like to try to show. So you're given this, now we have to sketch it. 0 to 1, 0 to y cubed. Oops. Yeah. And it's 3y cubed x squared. Yeah, it's y squared, so it's not the nicest integral, but we can do this. Saying, yeah, we do 2 pages for this. So y equals 1 implies that x equals 1 squared equals 1. How do I write that? Right, because the upper saying, yeah. Yeah, so x equals y squared will be like that. Yeah, not making anything complicated here. X equals y squared will be, we've done that before. And x equals 0. It's going to be bounded by those two curves, that line and that curve. Then y equals 0 and y equals 1. So it's this little area here in black. We have 1, 1, and 0. 0 are like the points, those, but it's not too relevant for this one. So yeah, we have to be a little bit tricky. So e to the xy dx. We basically do u substitution and such, and substitute in. And I even the limits changed around. Point is that we get it eventually, so it's u equals y cubed and u equals 0. Your limits e to the u. It's 3y cubed divided by y, and it's dy. So in the end, we start going further with this. So it's e to the y cubed minus e to the 0 dy. Eventually you get, yeah, e y cubed minus 1. We're going to leave it in that form and have 3, so I'm still dividing by y. So 3y squared times e to the y squared minus 1 dy. Then I guess we multiply it in now. 3y squared e to y cubed minus 3y squared dy. And I decided to do it like this, and I'm just going to separate these, because you can separate addition and subtraction, we can easily separate. I don't know if you have to really, but I decided to just do it to cut our losses. So same limits, it's just subtraction of this, and we got 3y squared. So 3y squared e to the y cubed dy. We can integrate that. We have to do another u substitution. You can use another letter if you want to be picky. Use another letter. Call this u2 and u1 or whatever for the different ones. You can do v now, I don't care. So throughout all this work, you eventually get e to the u du again. Then you can integrate that, get e to 1 minus e to the 0, so that's e minus 1. That's this part, the harder part to integrate. Now we integrate the other part real quick. 3y squared minus 3y squared dy, so that's 3 times the integral of y squared dy, basically. Y cubed over 3. Eventually you get 3 over 3, which is equal to 1. So we have e minus 1 minus 1, basically. Because it's a subtraction, we had to keep that subtraction between the two in one way. So it's e minus 1 minus 1. That's equal to e minus 2, so the whole integral is equal to e minus 2, and you can plug in e to calculate and subtract 2 from it and see what happens. Get that value if you need it. Okay. So for these ones, we're just switching the order, I believe. We're just switching the order I wrote down. We have some of these. This is important because it is sometimes easier to take it one way and not very hard to take it the other way. Integration. It's good practice to figure out how to take your domains. I might sketch this region twice to make it better. Yeah, we also sketched the region doing this. So you have your region here from this first one, dy dx. You have to write it as dx dy, something like that. So 4 minus 2x is y equals that. But x will be equal to 2 minus 1/2 y. And y equals 2 is at a limit, so obviously that's why it's drawn like that, the line here. And x equals 0, x equals 1, as I said. So you have 3 straight lines and one, sloped line. I know where it ends and intersections and all that, however you want, but yeah, 1, 2 will be an intersection. And also 0 and 4. 0, 4. X equals 0 line. But that's just keeping it simple here. So how you do this, generally speaking, when we want to switch them, you do it like before in writing those two cross sections. We kind of did it there. You have to draw it based on the first integral and then just change it based on your different cross sections that you take. So that's what you do. Otherwise, yeah, you had solvent for x. Give one of your in limits from y equals 4 minus 2x. Otherwise. So the trick here is it's kind of hard to explain. That's the problem with these types. Some things are harder to explain. So 2 to 4 is your y in this case. The reason for that is x equals 0 means that y equals 4 minus 2x becomes just 4, and x equals 1, it becomes 2. Oh, and you can see that from the graph as well. So y equals 2 and y equals 4, your y limits. And x equals 0 stays that way, going from left to right. X equals 0, so that's the leftmost, from obvious reasons. And x equals 2 minus 1/2 y will be the right part, where it ends. 35. Same thing. So we'll get from this form to that, and this is how. So y is given as y equals 0 and y equals 1, and x equals y and x equals square root of y. Okay, a little bit more harder to draw. Try it. I at least tried it. I think it's not the best picture, but it's an attempt. X equals y will be a very simple straight line. Just slope 1. It'll be x equals 1, y equals 1, x equals 2, y equals 2, and so on. X equals negative 10, and y equals negative 2, and so 10, and so on for infinity. And x equals square root of y. Also can be said it's y equals, where is it? Yeah, y equals x squared. Y equals x is basically is how you switch them around. I want to put this in terms of y. So we get x squared and x as our limits for that, and 0, 1 will be the limits for x, as we'll see here. Because you find points of intersection, it's 0, 0, and 1, 1. Because that's where y equals, because x equals y and x equals square root of y. They have to equal each other, so y equals square root of y. So y equals square root of y is intersection, so 0 equals square root of 0 and 1 equals square root of 1. That's like the only points that will happen. And x equals square root of y will be under here. X equals y. And you can graph y equals x and y equals x squared on a calculator and see which one's below which. But when you do that, I draw it out. So x equals square root of y will be this pink line here. The brown is x equals y. And its square root of y is underneath it. And that applies to the opposite. That's why in this one, why is it? Oh yeah, so it's y to square root of y because when you go left to right in the original, you can clearly see you start off with x equals y. It's over here. and it ends with x equals square root of y will be the rightmost. Now we have to do bottom to top, so x equals square root of y. Oh wait, no, it'll be y equals x squared because we're doing it in terms. So x limits are 0 to 1, it's dy dx, so x comes first here. Because the intersection is 0 and 1, 0, 0, 1, 1, so x values are 0 and 1. Where it's bounded, that's the boundaries in this case. And x squared to x. X squared is the lower limit because here y equals x squared is in pink and it's below. You go from bottom to top, so y equals x will be above. And vertical, it's basically the vertical cross sections from before. So that's why. Now the equivalent one. 0 to 1, 1 to ex, and cy dx. So 0 is less than or equal to x, less than or equal to 1, 1 less than or equal to y, less than or equal to e to the x. So y equals 1 is equal to e to the x to find an intersection. ln e to the x equals ln 1, so x equals 0. Because ln 1 is 0. ln e to the x is x. So y equals 1 and they'll intersect at one point. Then y equals e to the x at point x equals 1. So x equals 0 will be 1, y equals e to the x, and x equals 1 will be e, because e to the 1 will be e. That's this little region. It's not a triangle even though it almost looks a little bit like it, but it's a curve. It has a curve. It's not a straight line. Triangle would have 3 straight lines, not 2 straight lines and a curved line. It's this little region in black. So we have x equals 0 and x equals 1. We want to turn this into x terms. So y equals e to the x means ln y equals ln e to the x. So x equals, so it becomes x. That's just x equals ln y. This brown line over the. So ln y will be on the bottom because it's this line to the leftmost, and the right boundary will be just x equals 1. And y will be 1 to e. It goes from 1 here to e. So really, you're picturing, because when x is defined, whatever's defined as a function, it's going to be a curve or whatever. That's how you have to think of it. There's the leftmost in this case, y equals e to the, it's x equals ln y, which is y equals e to the x, same thing with notation. That's curved. You can't just have it be exact. It can't be. It's going to change values throughout. All x equals 1 is a constant value. It's just that straight line, horizontal, vertical. I'm hoping this makes sense. How you do this. So 16x dy dx. So we're going from the y to the x being the type of cross section, vertical to horizontal. You have to think in those terms. So 0 less than or equal to x less than or equal to 3 halves, 0 less than or equal to y less than or equal to 9 minus 4x squared. Y equals 9 minus 4x squared will be, and you can use a graphing calculator, software, whatever, to get this graph. You need it. The peak will be 9. Go downward. You plug in x equals 0 and x equals 3 halves, as those are your bounds. You'll get y equals 9 and y equals 0. It's really it's a good region. X equals 3 halves and x equals 0. And y equals 0 is the other boundary. Drawn out. But besides that, so in terms of x, this becomes x equals square root of 9 minus y over 4. You can simplify that further to get square roots on the bottom and the top. You get, so x equals square root of 9 minus y divided by just 2. So this integral 0 3 halves 0 to 9 minus 4x squared, 16x dy dx. Oh yeah, you don't do anything for this. For this type of integration, you don't really change that. You're just changing the limits here, these limits of integration. So it's 16x dx dy instead, and it's 0 to 9. That's x, so that's y. Y will go from 0 to 9. 0 here to 9. And 0 is x, it starts here. the leftmost thing is 0, x equals 0. Then the curve is this thing. So the curve is to the right. So it's x equals 9 minus y, square root of that, divided by 2. Okay, one last thing, just a quick word problem. Find the volume of the solid whose base is the region in xy plane that is bounded by the parabola y equals 4 minus x squared, and the line y equals 3x, while the top of the solid is bounded by the plane z equals x plus 4. Similar to the last section, z equals x plus 4 is what we're going to be integrating by when we get this actual thing set up. And I sketched sort of the region y equals 4 minus x squared and the line y equals 3x. Y equals 3x, y equals 4 minus x squared. It's going to be this somewhat interesting region. I don't know if it's the best drawing, but it should be a little bit more dramatic. So you set 3x equal to 4 minus x squared, 3x minus 4 plus x squared equals 0, so it's x squared plus 3x minus 4 equals 0. And you can solve this without a quadratic formula. It's x plus 4 times x minus 1 is what it's equivalent to. Equals 0. So x equals negative 4, x equals 1. X equals negative 4 means that y equals 3 times negative 4 equals negative 12, and x equals 1, y equals 3. We do 3x. So x equals 1, that's x equals 1 means y equals 3, and negative 4 means negative 12. Negative 4, negative 12, and 1, 3 are the points of intersection between y equals 3x and y equals 4 minus x squared. The line cuts the parabola in 2 points, which makes sense. Straight line, go like that, it would make sense. But if it's going to intersect it, it can at most do 2. So we have 1, 3, and negative 4, negative 12. And we set this up. I chose to make the x coordinates x be like the one that's based, so x equals 1 and x equals negative 4 for that point, those limits. These lines, and y equals 3x, y equals 4 minus, since it's given in that form, that's why. No one have to mess with it anymore. So 4 minus x squared will be the top, 3x the bottom, because you go from bottom to top. Bottom to top. So 3x is obviously below this region, below the parabola's region here. It goes from bottom to top. So then we integrate it. We do the first the inner integral, and eventually we get negative x cubed minus 7x squared minus 8x plus 16, because it's a simple integral, I'd say. Yeah, it's x plus 4 times the integral of y, because it's x. We do it with respect to y here. We just multiply an x plus 4 by 4 minus x squared minus 3x. You multiply, you get 6 values, and you do it. Okay. My point is, you integrate this expression by x. It's going to be quick. And there's a lot of work here because I tried to do it. I do this by hand to get an exact value like that. In the end, you simplify it down to 625 divided by 12. And that's it for this section.